I think its overall energy required is more than 5%. It's my personal thought though. But assuming this is a huge energy, so definitely we need to look something, some alternative so that we can treat this wastewater within our minimum cost. So the production of electricity using microbial fuel cell was first demonstrated by Potter in 1911. It's more than 100 years for this technology. See, it was basically Dr. Potter. He only demonstrated using two beakers, and he saw some power. And but there was no much research on this area. Just this research is like around 15 years to 20 years max. This is a very new research area. In this microbial fuel cell, we use bacteria as a biocatalyst to oxidize organic and inorganic matter. So in general, any kind of fuel cells or these electrochemical systems, we use some catalyst, but here we use biocatalyst as a bacteria. Bacteria means the bacteria which is already present in wastewater or any organic material. So basically, it's a consortia that degrades the material, whatever it is, food for them, and they produce electrons and protons that form current and basically overall power. And they also treat that wastewater. And possibility at large scale electricity production from wastewater treatment plant is possible because if we develop some hybrid technologies, then we can definitely introduce such large scale reactors into wastewater treatment plant. So this is a bioelectrochemical system overall. If you see, this is a microbial fuel cell, and they have like two electrodes. One is anode and one is cathode. So, but overall microbial bioelectrochemical system is basically all about two electrodes in some kind of solution. So in anode and cathodes are important, and then inside they have some membrane. Depending upon membrane and feed, this bioelectrochemical system or microbial system divided into four categories, broad categories basically. First is microbial fuel cell, where we produce power. Then second is microbial electrolysis cell, where we produce some kind of chemicals using this technology. And then microbial desalination cells. So in this system, we have one more chamber where we put saline water, that is a salt water basically, and we produce some current and saline water to sweet water. So basically the idea of this technology is not to produce electricity, it's just desalination. And this fourth is a microbial solar cell, where we use light energy and we employ green bacteria, either cyanobacteria or algae, and then they produce basically this, they consume organics and forms electrons and protons. And it's overall some kind of for power generation purpose as well as wastewater. So this is all about two electrodes. So if you see, these electrodes are so important, and that's why it is necessary to develop high performing electrode material. So focus points in this small presentation. So I'll brief something about electromicrobiology, then construction material, system architecture, scaling of microbial fuel cells, and some conclusions. So how do MFC work? So MFC converts chemical energy available in bioconvertible substrate directly into electrical energy. So as I mentioned, we got two electrodes, so anode and cathode. On the anode side, we produce we develop electroactive biofilm that basically convert a chemical energy. Chemical energy means the energy which is available in the form of wastewater, that organic, and the bacteria consume that organics for their multiplication, and they produce electrons and protons, where electrons are basically flow through anode to cathode via external circuit, and the proton that are generated um, in anode chamber travels from anode to cathode and finally reduced at cathode side. So in bacteria, substrate are oxidized and electrons are transferred to respiratory enzyme by NADH and FADH. These are basically coenzymes, and this is how they produce electrons. And using the electron transfer chain, they produce ATP. This is ATP for their energy currency. And these electrons finally released to terminal electron acceptor, which is generally oxygen, not always, but generally oxygen in microbial fields. So I'll show you one small video how these electrons and protons basically produce. This video is taken from YouTube, so please take a look. It's a small video. So.
In the tricarboxylic acid cycle, oxidation of organic molecules results in production of reduced coenzymes such as A and H. These coenzymes which is
Hello. Sorry to disturb you, sir. Your voice is not coming properly. Hello.
Hello. So I played video actually. So no voice.
Sir. Okay.
So is it something wrong with video?
Sir, it is going on, but I thought there should be some voice also. That's why I was thinking. Okay.
Okay. So yeah, I just this is it's okay. I will continue. I understand. So this is about electron transfer chain, how bacteria produce electrons and protons, as I mentioned. And these electrons are transferred through three kind of mechanism. So basically, this is suppose anode, and these are electroactive organisms, and they basically produce electrons and protons for power generation. So they have three different mechanisms. One is direct transfer. So direct transfers means they sit on electrode surface and they donate electrons, and then electron travels from anode to external circuit. Electron shuttling. So some bacteria, they use electron shuttling, some kind of electron acceptors, but they don't basically they are not necessarily attached to anode surface. And few are few are transfer these electrons using bacterial nanowires. So this is the classical way to donate electron at the surface. So geobacterial self-reduction is the prime organism to do this mechanism. So now I'll talk about something construction materials of microbial fields. So the ideal anode should be highly biocompatible, large electrochemical surface, and highly conducting and low cost. So biocompatibility is required because we deal with microbes. So we don't want any kind of toxic anode, and that's why it should be biocompatible. And large electrochemical surface means higher the electrochemical surface, so higher will be the electroactive biofilm coverage. And that's why we need some electrode material that has high surface, and also highly conducting material. So basically, if conductivity is higher, so electrons, whenever they donate electrons, the electrons should easily pass through external circuit. And of course, low cost, because these microbial fuel cells are not that highly performing, so we will not get in current in amperes. So we have to think for the cost first. And since we are working on very high surface, uh, um, this microbial fuel cell for power generation. And the other side, cathode. So generally, platinized cathode is used for microbial fuel cell, but this is not practical, since this terminology or this research has came from hydrogen fuel cell. So we have to go with platinized, non-platinized, non-precious gases such as copper, ferrous, nickel, cobalt, or etc., or maybe even composites. And finally, is proton exchange membrane. So generally, we use polymer electrolyte for research purpose, but ultimately we have to go with something different, because polymer electrolyte, uh, these are very thin membrane, and they are not like designed to withstand very high hydrostatic pressure. So I'll give some example of highly conducting polymers. First is polyaniline coating on stainless steel wood. So as I mentioned, we need to have very high surface area of material. So what we developed is we use stainless steel mesh, and we coated polyaniline using electrochemical deposition. And this is basically stainless steel. After the deposition, and you see here we form the nanowires on this surface, and these nanowires around 30 to 60 nanometers. This is a very thin nanowires for the electron conduction. Since it has very high electrical mobility, that's what we found this is the best material, and we further analyzed in microbial fuels. So after developing several small reactor, we constructed 18 unit microbial fuel cell stack for power generation as well as landfill leachate treatment. And we realized a very good performance. So our idea was to develop something that can give 12 volt, because generally 12 volt is a battery application. And we consider this as a bio battery for some kind of uh, low low energy consuming energy, some small electrical instrument. That's what these 18 cells were considered, because one microbial fuel cell can give around 7 to 800 millivolt as an open circuit potential. That's what we consider this. Here, if you see, in each slit, we use this anode material, and this is the cathode material. But here we use polyaniline plus some kind of like mix composite cathode material. And here is a few. Sorry. Here is some results of variation of bioelectrical performance of each cell. So as I mentioned, one microbial fuel cells can give around 6 to 700, even sometimes 800 millivolt open circuit voltage. Since we use landfill leachate as our substrate, so potential was relatively low, but we added extra cells to compensate the overall potential. So in the first graph, this is potential from all cells, and then later we combine. Uh, uh, we combine. This is the potential. So if you see, it's more than even 12 volt for 54 days, and then after that it started decline because no more like organics. So on the other side, we considered of individual current from individual microbial fuel cell, and this is the sigma overall, the sum of um, current of these microbial fuel cells. So this is basically a stack. And if you see, 70 milliampere current was produced. It was pretty constant for almost 3 months, 84 days. And this is the polarization behavior of individual microbial fuel cell and overall stack. So if you see the variation, this is quite possible because like we cannot make exactly all cells that can perform the same. If you see, this is the maximum power we found from each cell was 250 milliwatt, and then around 11 volt. And we also studied the leachate treatment. What was the efficiency overall? So here is the untreated leachate. So basically, the untreated was 200, 2200 milligram per liter. That was the COD concentration. And using this microbial fuel cell with various cycles, we could reach from individual cell around 600 milligram per liter. And this is the commercial aerobic treatment leachate. So this is this line. Basically, the commercial plants can go up to this. And this is the overall scenario. Like when we consider as a whole system, and we took samples from whole system, so you will see using the constant resistance mode, it was close to a commercial aerobic treatment plant. So wherever we got this sample, so it was not that we couldn't reach to that point, but we could reduce from 2200 to 250 milligram per liter. That was quite fascinating. So this is about the treatment, because the landfill leachate is a it was highly toxic, but this like particular microorganisms can even consume that kind of a toxic leachate. And this is the Coulombic efficiency of the system. So this graph is from individual, but if you focus this overall cell, so the Coulombic efficiency was 35%, and it was relatively less because we had only small cathodes from all over the site. So that was the reason. So we consider this in further development. So highlight of the study was basically the integration of 18 individual microbial fuels with polyaniline modified um, stainless steel anode and air cathode. So the individual microbial fuel cell achieved maximum open circuit potential with the landfill leachate ranging from 0.67 to 710 volt, and the total open circuit voltage we could attain was 12.8 volt. And the proposed stack of MFC was effective in removing uh, 86 to 87% chemical oxygen demand. The achieved performance of the stack MFC also suggests that it can be successfully developed in landfill leachate site for power generation and effective COD treatment. Because the COD treatment we achieve, that is quite fascinating. And with aerobic treatment, we put a lot of efforts in terms of money and energy to treat that wastewater, like around 200 milligram per liter. So definitely it is this kind of contribution can be deployed in such a commercial wastewater treatment plant. So in second phase, we basically scaled up this wastewater treatment process using this kind of microbial fuel cells using stack. So as I mentioned in previous version, we use a three-sided cathode assembly, but since the cathode was relatively low surface area as anode, so we couldn't achieve better Coulombic efficiency. So we developed microbial fuel cell stack. So here we further enhance our focus using two-stage system. One was basically We introduced a stage one for enhanced settling tank, so where we developed this enhanced settling tank microbial fuel cells, and then finally the second stage where we get the treated, partially treated wastewater, and then we finally fed to microbial fuel cells tank. So this was the preliminary design. So we had anode and cathode, and we put a wastewater, and then finally this is a continuous process. So wastewater will come, and then it will basically send to further stage, that is the microbial fuel cells tank. And it can remove basically stresses of solids. So it acts as a anaerobic, even anaerobic chamber, and also it acts as an oxygen scavenger, because we cannot control oxygen which is dissolved in wastewater, because oxygen is lethal for microbial fuel cells. So we don't want oxygen to go inside in a real microbial fuel cell. That's why this system is basically also capable of scavenging oxygen. And this is basically pre-treatment. And in second stage, we develop this microbial fuel cell. So these microbial fuel cell basically inspired from hydrogen fuel cell. It has a bipolar plate. This is a cathode, and the opposite side is an anode, or vice versa. And we basically developed into, again, 18 cell stack, like similar to previous studies. But here we introduce a high surface cathode as well. So using this microbial fuel cell study, we understand very high Coulombic efficiency, as well as COD removal up to 80 to 95%, and we improve Coulombic efficiency from 35 to 69%. So that was almost double. And now we are basically testing this microbial fuel cell for higher power output, and we are basically running a mini computer, like, for charging purpose. Like right now we can't use as a continuous power source, but we are basically charging a mini computer, and we are getting a very good potential and current. So the conclusion and future direction. So basically, these polyaniline, that are the conducting polymers, proved best and cheap anode material available so far using this microbial fuel cell. I'm saying because we use stainless steel wool, that is the very low cost, and even the synthesis of polyaniline on stainless steel itself is again a cheaper overall process. But the major challenges from MSS stack is to overcome proton transfer from anode chamber to cathode. That's a major challenge we are currently facing. So we are working how this mass transfer can be enhanced further. That is our prime focus. And from our bench scale studies, we can say that promising biotechnological invention for power generation and wastewater treatment. And absolutely system architecture and non-precious metal catalyst needs to be further understood, because we cannot use platinum based catalyst on cathode side. So these are few things. And this is our group. Basically, I work with IIT Bombay, Monash University, and got a grant from Bill and Melinda Gates Foundation. And currently I'm working at Laval University, where we are developing this, electrode materials, as well as we are basically trying to understand how bacteria electrochemically as well as microscopically respond to various materials. So this is some short presentation. So thank you very much. If you have any questions, so please ask.
Thank you very much. Thank you, sir, for your nice presentation. And I can say that it was a really great presentation because you have elaborated all the things in much detail. And maybe that's why we don't have any question in the chat box. So I can see Dr. Soumya is here. Are you listening with Dr. Soumya?
Yeah. Oh, sorry.
And Dr. Soumya, are you listening me? Okay, maybe some problem is there. So thank you, sir, for being with us. So now let's move to the another speaker. If he is ready, Dr. Sadiq.
Thank you very much.
Yes, ma'am. Yes, ma'am. I'm ready, ma'am.
Oh, okay, sir. Just so thank you, Dr. Jayesh. Now
Thanks.
we are moving to the second speaker. So our second speaker is Dr. Mohammad Sadiq. He is assistant professor in the Department of Physics, ARST College, Delhi University, and his research interest is solid state ionics, polymer electrolytes, polymer nanocomposite electrolytes, application of energy storage, conversion devices, lithium ion battery, solid polymer electrolytes, blend polymer electrolytes, and many more. So thank you, Dr. Sadiq, for accepting this invitation to deliver the invited talk. Now this dice is yours.
Okay, thank you, ma'am. I will share my presentations. I think presentation is here now, ma'am.
Dr. Jayesh, can you please uh,
One minute.
stop sharing your window? Yeah, so that Mr. Sadiq can share it.
I already. One second.
Yes.
Yeah, still we are seeing your.
Oh, I don't know. Like,
Your window.
okay, I will leave
Okay,
and I'll again.
no, sir,
I'll.
it's okay. No, it's okay, sir. Now we are seeing Mr. Mohammed Sadiq window only.
Okay.
Yes,
Okay.
sir.
Perfect.
Please
Now it
start.
is now it's here now, ma'am.
Yes,
If it
sir.
is
It is
PPT
visible.
is PPT is visible.
Yes, sir. It
Okay.
is visible properly.
Thank you, ma'am, for your kind invitations. And today my topic is development of polymer-based electrolyte for the energy storage and conversion device applications. And introductions to my research area. My research area is experimental condensed matter physics, and the sub area is solid state ionics. And this solid state ionics for the solid material as well as the polymer materials. And we investigate the physicals and the chemical behavior of the solid for the and also for the super ionic solids and the solid electrolyte or first ion conductors. These are the some overview of the energy storage and device applications and devices. Here now we are overall world is crisis, and the demand of this energy storage is day by day is enhanced. So we are highly used for the batteries and the supercapacitors and the fuel cells. But our aim is to prepare for the polymer-based electrolyte for the batteries and supercapacitor applications. And these are the some models. And now another one is the progress in storage technology, and these are the some brief overview of the energy storage for the in the basis of the first this polymer electrolyte was Professor P.V. Wright's in 1973. Then after Professor T.T. Takasaki in 1970, and and then come some technological experts. This polymer nanocomposite electrolytes was being seen in 1990s, and these are the some discovery of polymer electrolytes as well as the batteries. Another one is same lithium polymer batteries was in 1995 and this MIT also shows some in 2002 some polymer based electrolytes, and these are the some polymer batteries technologies with air bias and their energy density and rechargeable lead acid batteries and rechargeable nickel cadmium batteries and their energy densities watt per, and the problems in these lithium batteries are we cannot use without any purpose for lithium. So these are the also some technological applications of the lithium batteries as well as nickel ions and all the batteries applications. And this is the mechanism how batteries work. And we have a positive electrode as a cathode and negative as a anodes, and in between we have a separator. This separator may be liquids or gel polymer electrolytes. This is how lithium ions are stored in the lithium batteries, and this is the rayon plots specific energy density versus the volumetric energy for the smaller size, and this lithium is batteries are nowadays in all commercial aspect, and it's but there is some problems with the liquids electrolytes and how electrolyte work. And this is the cathodes, and this may be metals, and we have a graphitic anode layers in between, so we sandwich the electrolytes, and these lithium ions are intercalated with the this graphite sheets, and in between they are having a chargings and discharging profile is shown. Okay, and why this electrolyte is so important in the battery applications, and as you know that they are having some problem with the polymer based electrolytes, and that is conductivity problems, and in the cases of this liquid electrolytes, they are high hazard. In the cases of the liquid electrolyte, this liquid electrolyte having some problem with leakage issues and storage, all these issues, so that people are doing in a polymer based electrolytes, because and this is the brief overview of the batteries. And batteries we have anodes and cathodes in between separators. Our focus is on the electrolytes, and this electrolyte may be liquids or polymer based electrolytes. So in this study, we have to deal with the polymer based electrolytes, and this polymer based electrolyte is the polymer salt complex, ionic liquid based polymer electrolyte, gel polymer electrolyte, and the solid polymer electrolytes. In this solid polymer electrolyte, we used this nanofillers, and just like a titanium oxide, SiO2, TiO2, and ZNO and BaTiO3, and this clay base is this MMT monomonatite clay, and we also use the nano rods and nano wire for the fabrication of the solid polymer electrolyte. Similar way as the ionic liquid based polymer electrolyte, we use some plastic sizer agent to enhance their conductivity as well as mechanical stability. And polymer salt also, we having some different kinds of salt, inorganic salt, and just like lithium perchlorate, lithium hexafluoride, and also we have used some sodium salt. And these are the some drawback of the liquids and the gel polymer electrolytes. And we have in the cases of liquids electrolyte temperature range and corrosions of the electrodes problems and dental growth from the anode to cathode, bulky size and flammable solvent, poor mechanical stability. Similar and this gel polymer electrolyte poor interfacial properties, plastic size react with these electrodes, and these are the some issues. Similar and a brief overview of this solid state ionic conductors. And first, this is the frame of crystalline solids, ion conducting glasses, and polymer salt and polymer composite. Also, we focus on the polymer electrolytes, that is in polymer electrolytes liquid solid polymer electrolyte we are focused. And in this solid polymer electrolytes this have a broad category, dispersed type solid polymer electrolyte and exophobic and intercollected based polymer electrolytes. Why this solid polymer electrolyte is important? Because safety and secure storage device and no possibility of leakage, press lower cell price and weight issue, and shape of the flexibilities, improved short resistance for the better packings, and no memory effect and prevent for the thermal runnings. And their advantages and their challenges for the solid polymer electrolytes is to how to enhance the ionic conductivity and how to suppress the concentration polarizations, how to achieve the voltage, thermal and mechanical stability, better mechanical and thermal stability, and to improve the interfacial contacts between the electrodes and electrolytes. And another one is this polymer nanocomposite electrolytes. Nanocomposite is a combination of two or more different materials that are mixed in effort to form a blend. Why we choose this nanocomposite based electrolyte? Because we have to enhance the conductivity as well as the better mechanical stability. So that we are trying to doping some nano base filler. And why we used this nano base fillers? Because we improve the electrical properties as well as less cost and easily preparation method, and improve thermal stability, better control over the physical design parameter, and increase the polymers area for the. And these are the some technological applications and states of the arts. What are the parameters to be a requirement for the polymer electrolytes? First one is the ionic conductivity. In the current status, some polymer shows 10 to the power of 6, but the requirement is 10 to the power of 2 to 10 to the power of 4. And lithium ion transfers, and this is around 0.99 and 0.90 and 99, and this electrochemical stabilities window issues and tensile strengths, glass transition temperature, and Coulombic efficiencies. Because of this, they are having some research gaps, concentration polarization issues, polymer intrinsic viscosity, poor interfacial properties, and polymer blends. In order to fulfill this research gap, innovative approaches of the blend polymers and with some uniform dispersion of nanofillers and with some modified nanofillers and nanochelate, and we have adopted. These are the some literature. how the materials selection criteria for polymer, host polymer, salt, and nanofiller. And these are the some selection criteria to choose the polymer, salt, and filler. Our study, we have prepared the preparation of blend polymer based on PVP and PVA, and with several concentration of salt, and also we disperse the nano filler, and that is RGO, in a different weight persons, and we also prepare the biopolymer electrolyte, that is cellulose acetate with some magnesium salt. This is the how to prepare the polymer electrolytes. First, we take the host polymer as a PVP with some DI water and stirring for few hours, and then added some another polymers, and that is PVA, and in a doping in this PVP and stirring for 1 hour, and then finally we get PVP PVA blends, and then we can optimize the different weight persons, different concentration of the salt, and again stirring for 2 to 3, 6 to 7 hours, and then finally we get we can take in a petri dish for vacuum ovens and drying, and finally we get a freestanding polymer electrolyte film. And we have to confirm several technique used in this polymer electrolyte films. First one is the XRD. XRD is to confirm the composite formations and understanding the polymer salt and nano interactions, and to calculate the crystallinities and interchange separations. And in XRD, we have to confirm the intercalated, dispersive, or exophobic types of the nanocomposite. And another one is FTIR spectroscopy, and to probe the ion dissociations, associations and dissociation for the free ion pair in the polymer matrix, and to determine the function group present in the polymer matrix. And then we have to find out the thermal differential scaling calorimetry for the thermal study. And impedance study is to find the ionic conductivity of these blend polymer electrolytes, and we also check the ion transfers and linear sweep metric for the voltage stability of this polymer sample. And thermodynamic analysis is to find out the thermal stability of the material, and we have to check the voltage, check the UV visible spectroscopy. It helps to understand the band gap of the material, and also we have to check the voltage stability of the polymers electrolyte with cyclovoltammetric technique. And this one is our paper, and these are the some preparation technique with this XRD pattern shows that there is having some amorphic natures which reflect the conduction mechanism. This is the field FESN, the morphology of the prepared polymer sample. In this image, if we increase the salt concentrations, the morphology of the polymer films drastically change due to the dropping of the polymer salt complex. Also, we confirm this technique by our FTR spectrums. In this spectrums, where we have to find out the various bond mechanism of the polymer with salt and their assignment modes. And in thermal analysis, we find the differential scanning calorimetry to find out the crystallinity of the polymer. If we increase the concentrations, their crystallinity also increase. And also we have to take the band gap analysis of these polymer electrolyte films. And as we increase the concentration, this band gap also increase. That is why our conductivity is also increased as the concentration increase. This is the impedance spectra of the polymer films. And in order to that, our conductivity is the order of the 10 to the power of 5, but with polymer salt complex. And these are the some literature we compare with our conductivity with the literature. And also we find some dialectic parameter to analysis the dialectic properties of these polymer electrolytes. And suppose we take the tangent delta plots, and we find out the how the relaxation frequency of this polymer electrolyte film. These are the parameters we find the relaxation frequencies and their angular frequency. And also we have to find the modulus study. In modulus study, we have to find the some semicircle arcs in our in the beginnings. That is why in this we think that this will gives the more informations about the conductions mechanism. And also we find the cyclic voltammetry study. This cyclic voltammetry study is to find out the voltage stability of these polymers electrolytes. As we increase the concentrations, our stability of the electrolyte is to be increased. Similar, we compare with the linear cyclic voltammetry, and we check whether this system is correct or not. Also, these are the some conclusion part of the above summarized work. Another one is we have to take the investigations on the structural, opticals, and dialectic properties of the nanocomposite based electrolyte film. In this study, we have to synthesize and characterize of the dispersed type nanocomposite film. Here we take the similar point of PV and PEG, and we take the different weight portion of the RGO doping in the polymer salt complex. Then we take the first is to confirm the XRD. And we have in XRD we find various parameters for in this analysis. Again, we have find the FDR analysis for the band informations and polymer interactions and polymer ion interactions and their band analysis. This is the morphological image of the polymer nanocomposite film. In this case of the pure PVA and pure PAV with some doping of the RGO based nanocomposite film. As we increase the concentration of the RGO, and this morphology of the polymeric films is drastically changed, and due to the increase of the RGO contents. And here we also find the optical parameter for, and as well as the and thermal analysis, and also we find out the electrical parameter for the conductivity measurements. Again, we have to find out the cyclic voltammetry study for the various cycles, and in this case, and also we have to obtain the voltage stability window. As we increase the concentrations, the stability of the electrolytes is to be enhanced. So it means that is feasible use for the energy storage applications. And this is the broad mechanism of the energy storage applications, and we can check the ion transfers for the sample of 5 weight persons and the 2 weight persons. The ion transfers number is 0.98, which is used for the energy storage device. And this is the conclusion of our talk. And in this study, we enhance the stability of the electrolyte. And another one is we have to find out the electrical and dielectric properties of this study also. And we find the relaxation parameters and angular frequency and the DC frequency also check with a particular temperature, at the room temperature. Also, this is the summary of the above conclusion point. And also one study, we also check the biopolymer based electrolytes. In biopolymer based electrolyte, we take the cellulose acetates. Cellulose acetate as a biopolymers, and magnesium salt as a magnesium as an inorganic salt. And we take here for different concentrations of the magnesium salt as well as the biopolymer cellulose acetate. And similar way, we have to use the synthesis for the preparation by solution cast technique. Finally, we got a freestanding films, and then we check whether this films is used for the energy storage device applications. And this is the, and also we check the thermal analysis of the biopolymer electrolytes. And also we have to find the FDR analysis. In FDR analysis, we check the assignment mode for the various band mode. In FDR analysis, we have various symmetric and asymmetric mode are available in our sample. And also we find the band gap study, and we also check the impedance analysis. In impedance analysis, we obtain the ionic conductivity is the order of 10 to the power of 4, and also check the cyclic voltammetry parameter for the study of this cyclic for the application of the energy storage device application. And thermal linear sheet voltammetry is to find out the voltage stability of the polymer electrolytes. And these are the some summary of our work. And another study, we have some polymer based nanocomposite electrolyte. Why we choose this polymer electrolyte? What are the advantage of the polymer? Advantage of the nanofiller. The advantage of this nanofillers is to improve the physical properties or and improve the electrical properties also. Another one study is we take the PEO as a host polymer and paint, and we take the lithium LiPF6 as a lithium salt and different concentration of the DMMT modified clay. These are the some structure of the modified clay as well as the lithium salt. In this case, again, we take the FTR analysis for the various band informations and also we deconvolute these patterns to find out the free ions and cation ratio. And these are the some applications and these are the publications. I would like to thank my supervisor Dr. Javed Ali and my colleagues Dr. Yogesh Kumar and Professor S. A. Hasmi for their supporting during this research work, and my administrative support for my principal Professor Yantosh Kumar Jha. Without the PSLF, I will not do this work. And thank you for listening.
Thank you, Mr. Thank you, Muhammad Sadiq sir. Thank you, sir, for covering vast area towards this polymer electrolyte. And you have covered from existing problems to material selections and finally development of polymer electrolytes and their application in devices. So
Yes,
you have
ma'am.
already, yes, sir, you have already covered all the whole area, and you have explained everything, which certainly going to help the researchers who are working in
Yes,
this area.
yes,
And
ma'am.
my research work is also same, so I could also certainly get benefited from your expert talk. So let me thank you formally for your for giving time to us. Now there
Thank
are
you,
few
ma'am.
questions. Yeah, sir. A few questions are there in the chat box. So there are many questions. So I'm not going to take all, but few
Okay,
questions
ma'am.
definitely I will take. So these are one by one. One is from Miss Neha, and she is asking how to recycle the solid polymer electrolytes.
How to recycle it?
Yes, sir.
Recycle means in terms of
Means is there any way we can recycle it, the same electrolyte we can recycle again to use them in the devices?
yes, ma'am. You have to recycle this device. If the parameter is enhanced, then it is very good for the device applications.
Okay, another
Yes,
question
of
is,
course. Of
yeah,
course, it
can,
will be.
yes, sir. Can we have different methods to prepare polymer electrolytes?
Yes, yes, a different method. We have a tape casting method, melt intercutting methods. We
Okay.
have a different types of method
Yeah, yes, sir.
used for
And
the preparation of polymer electrolytes.
okay, sir.
But this one is the simplest one. The solution cast technique is the simplest one to prepare for the polymer electrolyte.
Okay. So next question is from Professor P.K. Singh, and he is asking that how much conductivity is expected from electrochemical devices?
The order of conductivity is 10 to the power of 2 to 10 to the power of 3. Is highly
Okay.
used for the energy storage device.
Okay. Next question is from Dr. Anjali Singh, and she's asking what is the best way to improve the working potential window of a solid electrolyte? Means how
Best
we can
window.
improve? Yeah.
Yes, we can improve by different concentration of filler as well as different dopant of salt, and we use to check whether this parameter enhance the ionic conductivity of stability of the electrolyte.
Okay. So another question is also from Professor P.K. Singh. Before taking the question, let me request Mr. Arora Narendra, kindly mute yourself because lots of noise is coming from your side. Mr. Arola Narendra, can you mute yourself? Okay, the next question. Dr. Mohit Sahani,
Yes.
can you help us? Dr. Mohit Sahani, can you help us? Okay, the last question is from Dr. PK Singh, and he is asking that what is the role of humidity on conductivity?
Role of humidity.
Yes, sir. How it is going to affect
Role
the
of humidity. If the sample having some moistures, it means that they not show the conductivity much better. But humidity problem is a very serious issue.
Okay, so
that is why the lithium salt having more issue for the humidity problem.
Okay, so I'm not seeing any further question in the chat box. So let me finally thank you, sir, for giving presentation in this week-long FDP come workshop. This is our first session, which got over by two of the speakers' presentation. So now again we are going to collect in the evening session, which will start from 3 p.m. So formally, I am announcing the closure of this first session of this third day of this 1 week long workshop come FDP on quality engineering and technological advances in materials and devices. So thank you all for joining with us, and kindly join the evening session at 3 p.m. Thank you so much. I'm ending the session now. Thank you.
अब जा रहा है
காலையில சைன் பண்ணது அது போட்டோம். ஈவினிங் ரிப்போர்ட் ரிப்போர்ட் இந்த 2 அங்க போட்டுருங்க சார். என்ன ஒரு டன்னு தான் உங்கள்கிட்ட காடி தான் போனேன். கேமரால இருக்கு. அது போட்டேன்னா ஏன் இல்லத்து போயிட்டோம். ஐயா மேடம் நேற்று ரிப்போர்ட் அனுப்பிட்டாங்க மேடம். உங்களுக்கும் அனுப்பிட்டாங்க. அனுப்பிட்டாங்க பண்ணிட்டுங்க. பட்ஜெட் அவங்க இதா போட்டிருக்காங்க. நாங்க ஒரு தனி ஒரு போர்ட்ல போட்டுங்க. அந்த இடத்த ஏதாச்சும் கிளீன் பண்ணி ஏதாச்சும் இது பண்ணுங்களா மேடம்? இந்த கிரவுண்ட் ஃப்ளோர் டேபிள் வந்து எம்பிஏ டேபிள் மாதிரி போட்டுட்டுங்க. 4 டேப் போட்டுட்டுங்க. ஆமாங்க. அப்புறம் பேரண்ட் வர்றதுக்கு ஒரு 4 சேர் போட்டுருவோங்க. அதான் இங்கேயே கீழே. ஆமாங்க. அந்த மாதிரி போட்டுட்டு நம்ம இது பண்ணிடலாங்க. ஓகே. அப்புறம் அந்த டேபிள்ல பிள்ளைங்க ஒரு கிளாஸ் மாதிரி போட்டு கொஞ்சம் டீசெண்டா வரது இருக்கிற மாதிரி அந்த டெக்கரேஷன் கொஞ்சம் பண்ணி இது பண்ணுவோம். அந்த ஒர்க்கை நாங்கள் பார்க்கணும். ஆமாம் சரி நான் பண்ணிட்டேன். ஆமாங்க. கேட்டுக்கலாம் உங்கள்கிட்ட கேட்டு. அதெல்லாம் அந்த ஒரு நான் இப்ப அவங்கள வச்சு மீட்டிங் போட முடியும். காலையில ஓய்மரம் ஒர்க் இருந்தது முடிச்சுட்டு அவங்கள கூப்பிட்டு பண்ணிடுறோம். இன்னைக்கு அந்த ஒர்க்கை நான் பண்றோம். ஒரு பிஹெச் ஓய்மரம் ஆமா மேடம். ஒரு பையன்
எடுத்து வச்சிருக்கோம்.
அஞ்சாம் தேதி வந்தாங்க.